Suppose we have a matrix A, and we consider the equation AX equals 0, where this 0 here is the 0 vector. We would say that that particular kind of equation is what we call a homogeneous equation. And what we're going to see in this section is that the uniqueness of solutions to this equation reflects on the linear independence of the columns of A. So let's look at a few examples. So suppose we have this 3 by 3 matrix here, 1, 2, -1, 2, 4, -2, 1, 1, 1, and we want to consider the equation AX equals 0. First of all, I want to point out that this particular equation, this always has at least one solution. And if you'd like to think about that for a second, I'll encourage you to pause the video here and see if you can think about why that is the case, and maybe you can come up with that particular solution. So the idea is that if we let x equal the 0 vector of whatever size it needs to be, it depends on the size of A, but if we let x equal the 0 vector, then A times the 0 vector in whatever, of whatever size will equal the 0 vector of, whatever size it needs to be. And so this always has at least one solution. And if we think back to, systems of equations and their connection to these matrix equations, we know that when we talk about these kinds of equations, there are only 3 options for the number of solutions we might have. We could have no solutions, we could have one solution, or we could have infinitely many solutions. So when it comes to homogeneous equations, we are, essentially looking at just 2 possibilities. We could have one solution, or we might have infinitely many. If we just have the one solution, then we would say that that solution is unique, of course, and we're going to connect that to the linear dependence or independence of the vectors that make up the columns of this matrix. But we'll see that in a little bit. For now, we will attempt to see if we have other solutions to this equation. I will point out that we often call this particular solution the trivial solution. So, x equals the 0 vector is the trivial solution to this homogeneous or homogeneous equation because, again, we always know it is a solution. But let's attempt to find other solutions. So we can set up our augmented matrix. We're going to augment this with, in this case, the 0 vector in R3. We row reduce this, and you're welcome to attempt to do this on your own, either by hand or with a computer or a calculator. But if we row reduce this, we would end up getting this matrix. Okay. And we do actually see that we are going to have infinitely many solutions here. We notice that this third column does not contain a pivot. And so we know when we're solving equations like this, when we have a column with no pivot, and our last column does not have a pivot. Now, I will say that our last column here will never have a pivot. Our last column is just all zeros and will always be all zeros as we're row reducing. And so, we will never have a pivot in that last column. Remember that if we were to have a pivot in that last column, then this system would be inconsistent. And so we know the system is never going to be inconsistent because we always have at least one solution. So this all sort of tracks with what we were, kind of learning about earlier in the course. But yeah, so we have this, third column without a pivot. So that tells us that if our original variables in x were x1, x2, and x3, that x3 would be our free variable. And so if we're writing x1, x2, and x3 in terms of that free variable, we would have that x1 equals -3x3, and x2 equals 2x3, and x3 just equals x3. So we have infinitely many solutions for x. They are all going to be some multiple. X3 can be whatever we want. And so, the vector multiple would look like this, negative 3, 2, 1. And so we have that free variable. We have infinitely many solutions, and they are all going to be the scalar multiples of that vector negative 3, 2, 1. Another thing I would like to point out at this point is the fact that, since we're ultimately going to be talking about linear dependence and independence, the fact that these vectors are linearly dependent. We saw that in the previous video, that if we ignore that last column and just row reduce, that we would end up with a column without a pivot. And so that tells us that these vectors are linearly dependent. So the vectors making up the columns of A. So if we say that A equals, the matrix with columns v1, v2, v3, then this set v1, v2, v3 is linearly dependent. So that's another thing we can tell from this work here. In particular, we can actually come up with a linear combination of v1 and v2 that gives us v3. Let's look at another example of a 3 by 3 matrix and consider this homogeneous equation, ax equals 0. Again, we will set up the augmented matrix. And this one reduces to this matrix. And we do end up with a pivot in every column but the last. Actually, we can see that if x is just x1, x2, x3, we do not have any of those columns that are missing a pivot. So we have just one solution here. And unsurprisingly, that solution is just x1 equals 0, x2 equals 0, x3 equals 0. So that trivial solution, that x equals 0, is the only solution. And again, if we say that A is a matrix whose columns are the vectors v1, v2, v3, then one thing we can see here is that this set of vectors v1, v2, v3 is linearly independent. So a connection between the fact that this particular equation has either one solution or infinitely many solutions, and the columns of that matrix making up a linearly dependent or independent set. And that leads us into proposition 249. So if we do have this matrix whose columns consist of the vectors v1, v2 up through vn, then the following statements are equivalent. So this means basically that all the statements that we list out here are either all going to be true or all going to be false. So that's what we mean by the following statements are equivalent. So to begin with, we say that the columns of A are linearly dependent. And that is equivalent to saying that one of the vectors is a linear combination of the others. Essentially, our definition of what it means for vectors to be linearly dependent. The matrix A has a column without a pivot position. We saw that in the previous video talking about, when we can tell if vectors are linearly dependent or independent. And so this is one way to tell that based on pivot positions. The homogeneous equation ax equals 0 has infinitely many solutions, and hence a non-zero solution or a non-trivial solution. That's what we were exploring in this video here. And then the last one, there are weights C1, C2 up through Cn, not all of which are 0, such that C1v1 plus C2v2 plus ... plus Cn_Vn equals 0. This is essentially saying that we can have a linear combination of our vectors and get the 0 vector where not all of those weights are 0. And there are some books or resources that actually use this last bullet as the definition of what it means for a set of vectors to be linearly independent, or excuse me, dependent, and then independent would be that all of those weights would have to be zero. So you can kind of flip all of these around to talk about linear independence, and so you can think about what that would mean and what that would look like. And essentially, you could use any one of these as your definition of what it means for a set of vectors to be linearly dependent. Our book chooses, basically that second bullet, essentially, right? That one of the vectors in the set is a linear combination of the others. But as I said, I've seen books where this last one is the definition of what it means to be linearly dependent, and then the others are derived from that. But this proposition is sort of a nice connection between a bunch of different ways we might think about vectors being linearly dependent or independent, in connection with pivot positions of a matrix, in connection with the number of solutions to this homogeneous equation. So, depending on the type of information you have and what kind of question you're asked, you might take one of these viewpoints over another. But again, they are all equivalent. So you're sort of welcome to switch between, and encourage really to switch between, these different ways of thinking about vectors and this idea of linear dependence or independence.